the edge of the solar system, past the last planet, past everything we've ever sent a spacecraft to visit, there is a region of space so large and so full of material that scientists still cannot fully explain why it exists the way it does. It begins just beyond Neptune. It stretches outward for billions of miles. And inside it, right now, there are trillions of objects drifting in the dark, frozen solid, some of them circling the sun so slowly that a single orbit takes longer than 2 centuries. The models say this region shouldn't look the way it does. The numbers keep coming back wrong. Every time astronomers think they have a clean explanation, the belt hands them another problem they can't solve cleanly. Here is the picture. Our solar system, by every reasonable measure of how planets and debris form, should thin out and go quiet past Neptune. The material at that distance was spread too far apart, moving too slowly, too cold to clump efficiently into anything large. The math is clear on this. And yet what we actually find out there is a vast ring of frozen debris containing hundreds of thousands of objects bigger than 100 kilometers across, at least 5 dwarf planets large enough to be rounded by their own gravity, and a total population that NASA estimates in the trillions. That is not what the textbooks predicted. That is not close to what the textbooks predicted. This is the kind of problem that keeps planetary scientists awake, because the discrepancy is not small and the cations are not minor. The region is called the Kuiper Belt. It is named after an astronomer who, almost perfectly, predicted it existed and then changed his mind and argued it didn't. His name is on it anyway. The belt begins at roughly 30 astronomical units from the Sun, which is the same distance as Neptune's orbit, and it extends outward to about 50 astronomical units, with a second outer population pushing much farther still. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt spans a range of roughly 20 astronomical units. That number, in miles, is almost too large to hold in your head. What makes it genuinely unsettling is not just the size. It is that the belt is simultaneously too big and too empty. It contains far less total mass than the objects already inside it should have required to form. Something enormous used to be out there. Most of it is gone. What happened to it and why the solar system looks the way it does today is one of the deepest unsolved questions in planetary science. The answer involves migration, chaos, and a solar system that 4 billion years ago looked almost nothing like the one we live in now. By the end of this, you will understand exactly why the Kuiper Belt breaks the models and why that matters. Now we begin at the moment the Kuiper Belt stopped being a theory and became something real. In the summer of 1992, after 5 years of scanning a patch of sky that kept returning nothing, a team at the University of Hawaii found something small, faint, impossibly slow-moving at the outer edge of the solar system. The 2 people responsible were David Jewett and Jane Liu. Jewett had started the search in 1987, convinced that the solar system could not simply end at Neptune. The idea was not controversial, it was logical. Comets with short orbital periods had to be coming from somewhere. The math pointed beyond the last known planet, but logic and evidence are different things, and for 5 years the evidence refused to show up. Night after night, Jewett and Liu would photograph sections of sky, then photograph the same sections again hours later, then compare the 2 images by eye. Stars don't move. An object orbiting the Sun does. The technique was straightforward. The execution was grinding. Thousands of hours of telescope time, thousands of image comparisons. For half a decade, nothing that moved in the right way at the right speed. The difficulty of what they were attempting is worth holding in your mind for a moment. An object sitting 40 times further from the Sun than Earth is receives roughly 1,600 times less sunlight. It reflects a tiny fraction of that back. By the time that reflected light crosses 4 billion miles of empty space and reaches a telescope on Mauna Kea, it is almost nothing. The object they were looking for would be barely distinguishable from the noise in the detector. Any single faint smudge could be an artifact. What they needed was a smudge that moved, slowly and consistently, over the course of hours. At those distances, even a fast-moving object crawls across the sky from Earth's perspective. That crawl is the signature. Finding it meant staring at images until your eyes ached and trusting that the faint, barely there shift you thought you saw was real and not imagined. On August 30th, 1992, Jewett and Liu were at the University of Hawaii's 2.2-meter telescope. They had a candidate. Something in the images was shifting, slowly, precisely, in the direction and at the rate you would expect from an object orbiting far beyond Neptune. The object was designated 1992 QB1. It was sitting roughly 41 astronomical units from the Sun, just past the orbit of Pluto. It had an estimated diameter of around 250 kilometers. Not large by planetary standards, barely a speck. But it was there, it was real. It was orbiting the Sun in the cold dark beyond every planet humanity had ever named. The significance was immediate. Astronomers understood what they were looking at. This was not another oddity like Pluto. That had been absorbed into the canon of the solar system over decades, until it seemed merely strange rather than revolutionary. This was confirmation of something different. The solar system had a structure beyond Neptune. There was a population out there, not just one lonely ice world, but potentially a vast field of objects that had been sitting quietly in the outer dark since the solar system formed. The questions that followed were obvious. How many? How large? How far out did they go? Nobody knew yet, but the fact of 1992 QB1 meant the search had changed shape entirely. It was no longer a search for evidence that something existed. It was a survey of something confirmed. What made this moment so consequential in planetary science is hard to overstate. For decades, the model of the solar system had a clean ending. 8 planets, an asteroid belt between Mars and Jupiter. Then Neptune, the farthest giant, sitting at 30 astronomical units and marking the outer boundary of the Sun's family. Pluto complicated that picture, but Pluto was treated as an exception, a freak, an error the solar system had made. With 1992 QB1, the exception became a category. The solar system did not end at Neptune. It extended billions of miles further, into a region that had never shown up in any telescope image, never appeared on any classroom chart, had only been suspected through theoretical reasoning and the indirect evidence of comet trajectories. The map of the solar system had to be redrawn, and the redrawn version was much, much larger. Jewett and Liu kept observing. They kept comparing images. The method was the same. The patience required was the same. 6 months after the first detection, they found a second object. Designated 1993 FW, it was orbiting in roughly the same region, another small icy body in the deep cold beyond Neptune. 2 objects, same distance range, same general orbital characteristics. This was not coincidence, this was population. One object could be argued away as a stray, a wanderer thrown out of the inner solar system and parked in an unusual orbit by some ancient gravitational accident. 2 objects in similar orbits, in the same distant region, within months of each other, with limited telescope time and enormous amounts of sky still unsearched. That told a different story entirely. If they can't, LD find 2 in 6 months. The actual population was almost certainly vast. The surface area of the sky was large. The objects were dim. They were barely scratching the outer edge of what was detectable. And they had already found 2. The years that followed would bring thousands more, each one adding detail to the map, each one sharpening the question of what exactly had been sitting out there for 4.5 billion years without anyone knowing. But the moment the question changed was 1992. Within 6 months they had found a second one. The question was no longer whether this region existed. The question was how far it went and what it contained. The belt bears his name, but Gerard Kuiper didn't actually believe it was there. That detail tends to get buried when people tell the story of the outer solar system. Kuiper was a Dutch-American astronomer working at the University of Chicago, one of the most respected planetary scientists of his era, and in 1951 he published a paper suggesting that a disk of icy bodies once existed just beyond Neptune. His reasoning was mathematical. The solar system had to have formed from a broad disk of gas and dust spinning around the early sun. That disk didn't stop at Neptune. It couldn't have. The physics of disk formation required material to extend further out, and the question was simply what had become of it. Kuiper's answer was that it had condensed into small icy bodies, a population of leftover planetesimals that never got swept up into a full planet. The idea was logical, almost inevitable if you followed the math far enough. Then Kuiper revised his own thinking. And this is where the story gets strange. By the time he updated his calculations, Pluto's estimated mass had been revised upwards significantly. Astronomers at the time believed Pluto was a substantial body, possibly comparable in mass to Earth. If that were true, Kuiper argued, Pluto's gravity would have been powerful enough to scatter or eject most of the material in that region over the age of the solar system. The belt, he concluded, had probably been cleared out. It might have existed once, early on, but it was almost certainly gone now. He had proposed its existence and then argued for its absence, all within a decade. His name ended up attached to a region he thought was empty. This is one of the more interesting reversals in the history of astronomy. Not because Kuiper was careless, he was doing exactly what a rigorous scientist should do, updating his conclusions when the evidence seemed to change. The problem was that Pluto's mass was wrong. The estimate Kuiper was working with was off by a factor of more than 500. Pluto is actually far smaller and lighter than mid-20th century astronomers believed, nowhere near massive enough to clear a region that size. But Kuiper had no way of knowing that. The true mass of Pluto wasn't pinned down until 1978, when its moon Charon was discovered and astronomers could finally calculate the system's actual gravitational properties. By then, Kuiper had been dead for 5 years. What makes the irony complete is that someone else had gotten there first anyway. 8 years before Kuiper's 1951 paper, an Irish economist and amateur astronomer named Kenneth Edgeworth published a paper raising a nearly identical idea. Edgeworth was not a professional planetary scientist. He had no institutional affiliation, no telescope, no observational data of his own. What he had was a careful reading of the existing literature and a willingness to follow the logic of solar system formation wherever it pointed. In 1943, he wrote that the outer solar system beyond Neptune likely contained a population of small bodies, too thinly spread to have coalesced into a single large planet, but present in enormous numbers. He estimated the total population would be vast. He even suggested that these objects were the source of some of the comets that periodically swung through. Gee, the inner solar system. He was right on essentially every point. Edgeworth's paper was largely ignored. It appeared in a relatively obscure journal, was written by someone outside the professional astronomy community, and arrived during a period when the field had other priorities. Kuiper's 1951 paper reached a wider audience and carried the authority of an established researcher. So the region became the Kuiper Belt. Only in recent decades, as historians of science went back and examined the archive, did the gap in attribution become clear. Many researchers now refer to the region as the Edgeworth-Kuiper Belt, a compromise that acknowledges both contributions. The International Astronomical Union hasn't standardized a single name, which means the literature uses both, sometimes in the same paper. The deeper point here is not really about who gets credit. It is about what mathematical reasoning can accomplish, decades before any instrument is sensitive enough to confirm it. Neither Kuiper nor Edgeworth had any direct evidence for what they were describing. No telescope in the 1940s or 1950s could have detected an object at 40 AU. The faintest hints in the data would have been completely buried in noise. What they had were the equations governing how disks of material behave around young stars, and those equations pointed unmistakably outward. The disk had to have left something behind. The comets coming in from that direction had to be coming from somewhere. The logic was sound even when the observation was impossible. Jewett and Liu confirmed in 1992 what the math had been implying since 1943. The region was not empty. It had never been empty. Pluto was not the last object at the solar system's edge. It was the brightest member of an enormous, cold, dimly lit population that had been sitting out there, undetected, for the entire history of human observation. Kuiper's name stayed on the map. Edgeworth's name got added. The math had been right all along. The names just took longer to settle than the science did. The simplest description of the Kuiper Belt is this: a vast ring of frozen debris sitting just beyond the orbit of Neptune, circling the Sun at distances so extreme that light from the Sun takes 4 to 5 hours just to reach it. To understand what that means, you need one unit of measurement. Astronomers use something called an astronomical unit, abbreviated AU, which is simply the average distance between Earth and the Sun. That distance is roughly 93 million miles, 1 AU. It is the baseline number that makes the rest of the solar system comprehensible, because the solar system operates on scales that miles alone cannot adequately express. Mercury sits at about 0.4 AU, Mars at 1.5. Jupiter, the largest planet, orbits at roughly 5.2 AU. By the time you reach Neptune, the outermost planet, you are 30 AU from the Sun, 30 times the Earth-Sun distance. That is 2.8 billion miles. A spacecraft moving at 36,000 miles per hour takes nearly a decade to get there. The Kuiper Belt begins right where Neptune's orbit ends, at around 30 AU, and it extends outward to roughly 50 AU. That additional 20 AU sounds modest when written as a number. It is not. It means the belt stretches across a region more than 1 billion miles wide. The outer edge sits about 4.6 billion miles from the Sun. Beyond that, a second population called the scattered disk pushes outward still, with some objects swinging out to hundreds of AU on enormous elliptical loops. But the main classical belt, the dense donut-shaped ring that defines the structure, occupies that band between 30 and 50 AU, and it does so in 3 dimensions. It is not a thin line. It is wide, it is tall, and it is thick with material. Picture it this way. Neptune's orbit is already a circle with a radius of 2.8 billion miles. The Kuiper Belt wraps around the outside of that circle like a wide, flattened tire. The whole structure is tilted slightly relative to the plane of the planets, with objects scattered above and below that plane. Some are inclined nearly 20 degrees off the ecliptic. This is not a neat flat ring like the rings of Saturn. It is a sprawling, 3-dimensional cloud of objects shaped roughly like a donut, orbiting the Sun so slowly that a single trip around takes more than 200 years. Now contrast that with the asteroid belt, which sits between Mars and Jupiter at roughly 2.2 to 3.2 AU from the Sun. That belt is familiar enough that it has appeared in countless films and diagrams. It feels like the boundary between the inner solar system and the outer, but the asteroid belt is, in solar system terms, relatively compact and close. The Kuiper Belt is twice as wide and twice as tall, and it contains somewhere between 20 and 200 times more mass. That is not a small difference. At the high end of that estimate, the Kuiper Belt outweighs the asteroid belt by 2 orders of magnitude. There is also a compositional difference, and this one matters. The asteroid belt is rocky. The objects there are silicate, metallite, carbonaceous, the same stuff planets are made of. The Kuiper Belt is something else entirely. Its objects are icy, not ice in the sense of a frozen lake, but a mixture of water ice, methane ice, and ammonia ice, along with complex organic molecules and some rock. The temperature out there is roughly minus 369 degrees Fahrenheit, which is minus 222 degrees Celsius. At that temperature, compounds that would evaporate quickly anywhere near the sun stay frozen solid. They have stayed frozen solid for 4.5 billion years. That is when the solar system formed, and the material in the Kuiper Belt has been sitting undisturbed at these temperatures for essentially all of that time. This is one of the things that makes the belt so scientifically extraordinary. It is not just a collection of distant objects. It is a freezer full of primordial material, locked in a state that preserves the chemistry of the early solar system. The objects in the inner solar system, the rocky planets, the asteroids, have all been heated, battered, melted and reformed over billions of years. The Kuiper Belt objects have not. They are relics. Whatever they were made of when the solar system was young, they are mostly still made of that now. The surface conditions on a Kuiper Belt object are difficult to picture. There is no warmth. The sun from 40 AU away is about 1,600 times dimmer than it appears from Earth. It would look like a very bright star, not a disk. There is no wind, no geological activity for most objects, no liquid of any kind. Just frozen chemistry sitting in the dark at temperatures close to absolute zero, drifting along an orbit that takes centuries to complete. When astronomers describe the Kuiper Belt as beginning just beyond Neptune, that phrase, just beyond, is doing a lot of work. Just beyond Neptune is already the most remote place any spacecraft has ever traveled under its own mission plan. Just beyond Neptune is a region that took nearly a decade to reach at speeds no human being has ever personally experienced. And the Kuiper Belt extends from that already incomprehensible distance outward for another billion miles, holding trillions of objects, most of which have never been seen, in conditions that have not changed since before Earth existed. The asteroid belt, which most people picture as the wild outer region of the solar system, is a tiny warm puddle compared to this. Here is the problem that has been nagging at planetary scientists since 1992, the one that gets worse the more carefully you look at it. When astronomers confirmed the Kuiper Belt was real, the immediate reaction wasn't just excitement, it was confusion. Because the belt that Jewett and Liu had found, and that dozens of follow-up surveys kept filling in, was far larger and far more populated than anything the standard models of solar system formation had room for. The models weren't slightly off. They were off by a factor that made scientists go back to the beginning and ask what they had gotten wrong. Here is what the standard picture predicted. In the early solar system, there was a disk of gas and dust and small rocky and icy particles orbiting the young sun. Closer in, where temperatures were higher and material was denser, particles collided frequently enough to stick together, gradually building up into larger and larger bodies. This is how Earth formed. This is how Jupiter's core formed. The process is called accretion, and it works well in the inner solar system because there is enough material packed tightly enough that collisions happen on useful timescales. The problem, and this is the central problem, is that accretion gets dramatically harder the farther out you go. At 40 to 50 AU from the Sun, two things work against you simultaneously. First, the material in the disk is spread thinner. There is simply less of it per unit of volume, which means particles are separated by larger distances and collide less often. Second, the orbital velocities at those distances are much slower. An object at 40 AU moves at roughly 4.7 kilometers per second compared to Earth's 30 kilometers per second. Slower orbits mean it takes longer for any two objects to even find each other, let alone collide. Put those two effects together and you have a region where the pace of planet building slows to something that the timescales of the early solar system simply could not accommodate. The protoplanetary disk, the raw material from which planets form, doesn't last forever. The young sun's radiation and solar wind gradually blow the gas portion of the disk away. Most estimates put the lifetime of the gas disk at somewhere between 3 and 10 million years. After that, you are left with only the solid material, the dust and the already formed bodies, and you lose the drag forces that help small particles settle and stick together efficiently. 3 to 10 million years sounds long. At 40 to 50 AU, it isn't. Models consistently show that at those distances, the accretion process runs too slowly. By the time the gas disk disperses, objects at the Kuiper Belt's location should still be small, kilometer scale at best. There shouldn't be time to build anything the size of Pluto out there from scratch. There shouldn't be time to build the hundreds of thousands of objects larger than 100 kilometers that we now know exist. And yet there they are. This is the part that keeps planetary scientists awake. You can't dismiss the observation. You can't argue with the numbers. The Kuiper Belt is full of large bodies that should not have had the time or the material density to form where we find them. Some models attempted to solve this by simply scaling up the original disk. If you assume the primordial belt was 50 to 100 times more massive than it is today, you could in principle get enough local density to speed up accretion enough to work. But that solution immediately creates a different problem. If the belt started out with that much mass, where did it go? The current Kuiper Belt is estimated to contain somewhere between 1/100th and 1/10th of an Earth mass. If you started with 50 times more, you are missing a staggering amount of material with no clean explanation for where it ended up. One problem dissolves, and worse, one takes its place. There is also the geometry problem. The Kuiper Belt doesn't just contain large objects. It contains large objects spread across a region that spans billions of kilometers. The radial width alone, from roughly 30 AU out to 50 AU, covers a distance greater than the entire span from the Sun to Neptune. A ring that wide, with material that's sparse, is not a place where standard accretion builds large bodies efficiently. It is a place where the standard physics of planet formation essentially stalls. The density falls off with distance in a way that makes the outer edge of the belt especially difficult to account for. Objects sitting at 48 or 50 AU are even harder to explain than those at 35. Yet they are there. What this tells you is not that physics is broken. What it tells you is that the Kuiper Belt did not form the way we assumed planets and small bodies normally form. Something else happened. Either the objects we see didn't form where they currently orbit, or the mechanism that built them was fundamentally different from simple pairwise collisions between drifting particles. Probably both are true to some degree. The answer involves planetary migration, gravitational scattering on a solar system-wide scale, and a period roughly 4 billion years ago when the outer solar system was violently rearranged. The early solar system looked almost nothing like the one we live in now, and the Kuiper Belt is one of the clearest pieces of evidence for that. Its size and population are not anomalies to be explained away. They are signals pointing directly toward a history of chaos that standard models built from the inner solar system never anticipated. The Kuiper Belt is not just large, it is large in a way the early solar system should have made impossible. And that contradiction points somewhere very specific. When NASA says there may be trillions of objects in the Kuiper Belt, that number is both accurate and almost meaningless, because the human mind cannot hold a trillion of anything. A trillion is 1,000 billions. It is 1,000,000 millions. If you counted one object per second without stopping, you would be counting for 31,000 years before you finished. That is the scale of what astronomers are describing when they talk about the population of this region, and the honest answer is that nobody has counted anywhere close to 1 trillion. The trillion figure is an inference. It is what the models demand must be there, based on the objects we have actually managed to find and confirm. The gap between the confirmed number and the inferred number is one of the more quietly unsettling. Facts in planetary science. Start with what we have actually detected. By the time the Kuiper Belt had been studied for about 3 decades, astronomers had confirmed the existence of roughly a few thousand named objects. A few thousand, out of a potential trillion. The confirmed objects larger than 100 kilometers in diameter number somewhere between 35,000 and 70,000, depending on whose models you use. That range alone, 35,000 to 70,000, tells you something important. Scientists cannot agree on the count even for the largest objects, because even those are mostly too dim and too distant to find with certainty. The estimate varies by a factor of 2, which is not a rounding error. It reflects genuine uncertainty about how much of the belt we've been able to see. The reason so few have been confirmed comes down to a basic problem of physics. These objects are incredibly far away. At 40 to 50 AU, sunlight has already spread so thin that it carries a tiny fraction of the intensity it has near Earth. A Kuiper Belt object receives roughly 1,600 times less sunlight than Earth does. What light does hit the surface is mostly absorbed or scattered. Only a small percentage bounces back toward us. By the time that faint reflected signal crosses 4 to 5 billion miles to reach a telescope, it is almost nothing. A 100-kilometer KBO at 45 AU is roughly as bright as a dim light bulb at a distance of about 50,000 kilometers. The largest ground-based telescopes can detect it, but only barely, and only under ideal conditions. Objects smaller than that, which make up the vast majority of the population, are simply invisible to most instruments. There is a second problem beyond the sheer dimness. These objects move slowly. At 40 AU, the orbital velocity of a Kuiper Belt object is so low that from Earth it appears to drift almost imperceptibly against the background of stars. A KBO moves only a fraction of an arcsecond per hour across the sky. Stars, by comparison, appear completely stationary on those timescales. Identifying a KBO requires stacking multiple images taken hours apart and searching for a point of light that has shifted position against the fixed star field. The software that does this is sophisticated. The surveys that use it are intensive and methodical. Even so, the sky is enormous, the objects are dim, and the search has covered only a portion of the region. This is where stellar occultation comes in. When a Kuiper Belt object passes directly between Earth and a background star, it briefly blocks the star's light. The star doesn't fade gradually. It cuts out and comes back in fractions of a second, because the KBO has no significant atmosphere to cause gradual dimming. By timing that blink precisely and knowing the object's distance, astronomers can calculate its diameter. This technique has allowed size measurements for objects too dim to photograph directly. The results have filled in parts of the size distribution that direct imaging simply cannot reach. Objects as small as roughly 1 kilometer across have been detected this way, and the numbers at that size range climb fast. For every large object in the belt, there are vastly more small ones. The size distribution follows what scientists call a power law. Double the size threshold you're counting, and the number of objects drops by a predictable ratio. The distribution is steep. There are hundreds of thousands of objects larger than 10 kilometers for every object larger than 1,000 kilometers. There are millions of objects larger than 1 kilometer. Below that, the count climbs toward numbers that become genuinely hard to state. The smallest detected KBO found through occultation surveys sits at roughly 980 meters across, barely a kilometer. and there are almost certainly smaller ones that haven't been detected yet. At the large end, Pluto sits at 2,376 kilometers in diameter, the biggest confirmed object in the belt. Below Pluto comes Eris, at about 2,326 kilometers, which is so close in size that the two are essentially twins. Then Makemake, Haumea, Quaoar and others, stepping down through the hundreds of kilometers. These large bodies were genuinely unexpected when they started turning up. Before 1992, models gave no particular reason to expect a population of objects this massive this far from the Sun. Each discovery in the 500-kilometer range and above revised the picture further from what the standard formation models had described. The scale of what remains hidden is difficult to accept as a scientific fact rather than an admission of ignorance. Astronomers are reasonably confident that the confirmed objects account for something less than 1% of what the models require to be there. The surveys have been thorough by the standards of any previous era of telescope technology, and they have returned a catalogue that looks enormous by any human measure. Thousands of named objects, hundreds of thousands inferred in larger size ranges, trillions projected at small sizes, but the projection dwarfs the confirmation by orders of magnitude. The catalogue of confirmed objects today represents a tiny fraction of what the models say must be out there, hidden in the dark and the cold, too faint for any telescope we've yet built to resolve. There is a second problem layered on top of the first, and this one is almost more unsettling. You have just absorbed the population numbers, trillions of objects, hundreds of thousands larger than 100 kilometers, a region stretching across billions of miles with more material in it than the asteroid belt by a factor of 20 to 200. That is the size problem. The Kuiper Belt is enormous. Explaining why it is enormous has kept planetary scientists busy for 3 decades. But sitting underneath that problem is a second one that cuts in exactly the opposite direction. When astronomers actually try to weigh the Kuiper Belt, to add up everything that is out there and calculate its total mass, they get a number that is almost embarrassingly small. The current best estimates put the total mass of the Kuiper Belt somewhere between 1/100th and 1/10th of an Earth mass. Let that settle for a moment. The entire Kuiper Belt, all those trillions of objects spread across billions of miles of space, adds up to less than 1/10th of the mass of the planet you are standing on right now. This is not a rounding error. It is not a measurement artifact. It is one of the most documented and frustrating puzzles in planetary science, and it has a name. Astronomers call it the missing mass problem. Here is why it matters so much. The large objects in the Kuiper Belt, Pluto, Eris, the other dwarf planets sitting out there beyond Neptune, could not have formed in a disk this thin. To build something the size of Pluto at 40 astronomical units from the Sun, you need raw material. You need enough nearby mass that collisions happen frequently enough, gently enough, that objects can stick together and grow. The problem is that at 40 AU, everything moves slowly. Orbits are vast. The gaps between objects are immense. In a disk as sparse as the Kuiper Belt is today, the time it would take for random collisions to assemble something as large as Pluto is longer than the age of the solar system. The math simply does not close. So scientists worked backward. They asked, how much mass would the primordial disk have needed to contain for these objects to have grown within a reasonable time frame? The answer they kept arriving at was somewhere between 50 and 100 times the current mass of the belt. Maybe more. The disk that built Pluto and Eris was not a thin, sparse ring like the one we observe today. It was a dense, heavy structure, rich in material, with enough objects close enough together that accretion could proceed on a timescale that fits inside the life of the solar system. That primordial disk may have held somewhere between 10 and 30 Earth masses of material in the region we now call the Kuiper Belt. What sits there today holds, at most, 1/10 of one Earth mass. The numbers are hard to reconcile. Something took more than 99% of the original material and removed it. And it did not just remove small objects, it removed the overwhelming majority of everything, large and small, behind only the thin remnant we can observe today. Where did it go? That is the question. Several mechanisms have been proposed and none of them is clean. One possibility is that mutual collisions between objects became destructive rather than constructive. Early in the solar system's history, as the disk began to thin out and orbital velocities shifted, collisions that once allowed objects to accumulate and grow instead started breaking them apart. Grinding. Object hitting object at the wrong speed, shattering both into smaller fragments. That then collided again, grinding finer and finer until the debris was small enough to be pushed out of the solar system by radiation pressure from the sun. This is called collisional grinding. It is real, but it is not efficient enough on its own to account for this scale of mass loss. Another possibility involves gravitational scattering. If a large body, or several large bodies, move through the region during the solar system's early chaotic period, their gravity could have flung enormous quantities of material onto new trajectories, some falling inward toward the sun, some ejected outward into interstellar space. Jupiter is extraordinarily efficient at this. Objects that get nudged into Jupiter-crossing orbits are almost always ejected from the solar system entirely within a few million years. If the primordial Kuiper Belt fed material inward and Jupiter acted as a kind of gravitational drain, the mass loss rate could have been dramatic, but this mechanism requires something to do the initial nudging, something to destabilize those orbits and send material sunward in the first place. This is the point where the missing mass problem and the size problem stop being two separate puzzles and start pulling toward the same explanation. A belt that is too large in extent and too light in mass is not a contradiction, it is a signature. It is what you would expect to see if something very large and very disruptive had passed through, not a rogue star, not an external force, something inside the solar system itself, something that was part of the original architecture, that moved and in moving swept most of the material away. The belt survived that event, but barely. What remains is the residue of a much larger structure, preserved in the outer solar system like the debris field after something catastrophic passed through. The problem cannot be solved by looking at the Kuiper Belt alone. It requires understanding the history of the entire solar system during its first billion years, a period that was far more violent than anything observable today. A period that left its marks in orbital architectures and mass deficits and population distributions that planetary scientists are still trying to decode. The belt we see is a ghost of something much larger, and figuring out what happened to the rest of it has reshaped how scientists think about the entire early history of the solar system. The answer that has gained the most traction over the past 2 decades does not start with the Kuiper Belt at all. It starts with Neptune. In the late 1990s and early 2000s, a group of planetary scientists working in Nice, France, began building a model of the early solar system that looked almost nothing like the one we live in today. The model carries the name of that city. It is called the Nice model. Its central claim is both simple and radical. The giant planets did not form where we find them. Jupiter, Saturn, Uranus and Neptune were born in a tighter cluster, sitting closer to the Sun, packed into a smaller region of the disk. Then, over millions of years, they moved. Not randomly, not violently at first. They drifted, pulled and pushed by gravitational interactions with the vast field of planetesimals surrounding them, until something tipped the whole system into a phase of instability that reshaped nearly everything. Neptune is the key piece. In the Nice model, Neptune formed somewhere around 15 to 20 AU from the Sun, roughly half its current distance. Between Neptune and the positions of the outer planets, there was a dense disk of icy planetesimals stretching outward, containing far more mass than the Kuiper Belt holds today. Neptune was not sitting still inside that disk. It was slowly exchanging momentum with the objects around it. When Neptune scattered a planetesimal inward, it received a tiny gravitational nudge outward in return. Multiply that nudge by billions of planetesimals over tens of millions of years, and Neptune migrated. Slowly at first, then more steadily, it moved outward through the primordial disk, ploughing through material that had been sitting undisturbed since the solar system formed. What happened to that material is where the missing mass problem starts to find its answer. As Neptune swept outward, it scattered the planetesimals it encountered. Most of those objects were thrown inward toward Jupiter, and Jupiter, the most massive planet in the solar system, is an extraordinarily efficient ejector. An object that gets too close to Jupiter does not stay in the solar system. The gravitational interaction gives it enough velocity to escape entirely. Jupiter ejected the vast majority of the material Neptune sent its way. That material is simply gone, launched into interstellar space, never to return. This is where the mass went. The primordial disk may have been 50 to 100 times more massive than the Kuiper Belt is today. Jupiter systematically removed most of it over a span of roughly 500 million years. A fraction of the scattered objects were not ejected. Some were pushed outward instead of inward, nudged into orbits beyond Neptune's reach. Others were caught in resonances with Neptune, gravitational patterns where the ratio of orbital periods locks two objects into a repeating relationship, like a metronome keeping time across billions of kilometers. Pluto itself sits in a 3-to-2 resonance with Neptune, completing exactly 2 orbits for every 3 Neptune completes. It is not a coincidence. Pluto was captured into that resonance as Neptune migrated outward. So were hundreds of other objects, the ones astronomers now call Plutinos. The current structure of the Kuiper Belt, with its resonant populations, its scattered objects, its distinct orbital families, is the fossil record of Neptune's journey. This is the elegant part of the NICE model. It explains with a single mechanism why the Kuiper Belt exists in its current form, why it contains so much less mass than formation models require, why its population is sorted into the orbital families we actually observe. Before the NICE model, these 3 facts sat separately, each requiring its own explanation. After it, they become consequences of one event. That kind of unification is what planetary scientists mean when they call a model compelling. But compelling is not the same as complete. The NICE model immediately introduces questions it cannot fully answer. The most pressing is timing. For Neptune's migration to produce the orbital structure we observe, it needs to have happened on a specific timescale and in a specific way. If Neptune migrated too quickly, it would have scattered the cold classical Kuiper Belt objects, the ones with nearly circular, undisturbed orbits, into the chaotic jumble we see in the hot population. But those cold classicals are still there, sitting quietly, their orbits barely touched. Something protected them, or Neptune's migration bypassed them in a way the basic model does not cleanly explain. This is one of the live tensions in the field. There is also the question of what triggered the instability in the first place. The NICE model requires that the giant planets remain in their compact initial configuration for hundreds of millions of years before the instability kicks in. What held them in place for so long? And what finally pushed the system over the edge? One leading idea connects this moment to the late heavy bombardment, a period roughly 600 million years after the solar system formed, when the inner planets were pelted with an elevated rate of impacts, evidence of which is still visible in the cratered surfaces of the Moon. The hypothesis is that the giant planet instability and the late heavy bombardment were the same event. The timing works roughly, but the evidence is contested. Some recent analyses of lunar crater ages have raised doubts about whether the bombardment was ever as concentrated as the original data suggested. What the NICE model gives us, ultimately, is a framework, a story of migration and scattering that explains the broad architecture of the outer solar system better than any alternative. It is not finished science. Theorists are still adjusting the initial conditions, debating how many ice giants were involved, arguing over whether the instability was gradual or sudden. The migration model solves many problems and creates several others. That is the hallmark of a framework that is probably pointing in the right direction, but hasn't gotten all the way there yet. Inside the Kuiper Belt, there are at least two distinct populations of objects that should not have ended up in the same neighborhood, and the fact that they share the same region of space is itself a clue about what happened during the early solar system. The first thing to understand is what astronomers mean when they call these groups cold and hot. The names have nothing to do with temperature. Both populations sit at roughly minus 369 degrees Fahrenheit. Both are frozen solid. The terms are borrowed from physics, where heat describes the energy of random motion. A cold population moves predictably, smoothly, in ordered paths. A hot population has been stirred up, its orbit stretched and tilted by some outside force. In the Kuiper Belt, cold and hot are shorthand for untouched and disturbed. That distinction turns out to matter enormously. The cold classical objects occupy a narrow band between roughly 42 and 45 astronomical units from the Sun. Their orbits are nearly circular. They stay close to the ecliptic plane, the flat sheet along which the planets travel, rarely deviating by more than a few degrees. If you could watch one of these objects from above the solar system, it would trace a path that looks almost like a drawn circle, steady, unhurried, barely wobbling. These objects have been doing this for 4.5 billion years. Nothing has touched them. Neptune's migration swept chaos through the outer solar system, and somehow this population came through it largely intact. They sit today almost exactly where they formed, which makes them extraordinarily valuable. They are a direct sample of the primordial outer disk, preserved in place. The hot classicals occupy much of the same distance range, between about 40 and 50 astronomical units, but their orbits look completely different. They are stretched into ellipses. They tilt away from the ecliptic, sometimes by 10, 15, 20 degrees or more. An object in a hot classical orbit is ranging widely through space with each pass around the Sun, swinging closer and then retreating farther out in a long looping path. These orbits are the fingerprints of Neptune. As the planet migrated outward billions of years ago, it pushed gravitational waves through the disk ahead of it. Objects that got caught in resonances or close encounters with Neptune found their orbits kicked and tilted. The hot classicals are the objects that survived those encounters without being fully ejected. They were shaken, not removed. What makes the cold classicals genuinely strange is how different they look up close. Their surfaces are among the reddest in the solar system. That deep red color comes from tholins, complex organic molecules built up over billions of years as radiation bombards simple ices like methane and water. The longer a surface sits undisturbed in the outer solar system, the redder it tends to get. Cold classical surfaces are extremely red, which is consistent with objects that have been sitting quietly in the same place since the earliest period of the solar system. Hot classicals, by contrast, show a wider range of colors. Some are red, some are more neutral, closer to grey. That spread reflects a more mixed origin. These objects came from different starting locations before Neptune's influence shuffled them into their current orbits. Then there are the binaries. Cold classical objects have an unusually high fraction of binary companions, pairs of roughly equal-sized bodies orbiting each other at wide separations. This is not a coincidence. Wide binary pairs are fragile. A close encounter with a large planet would rip them apart. The fact that so many cold classicals are still in wide binaries tells you they have not had close encounters with anything. Their binary geometry is original equipment preserved from the moment of formation. Hot classicals have far fewer wide binaries. The encounters that stirred their orbits would have destroyed most paired systems. What survived tends to be tightly bound pairs that could withstand the gravitational jostling. The binary statistics alone are enough to tell you these two popular Attians lived very different histories. This is what makes the Kuiper Belt such a layered archive. From a distance, the classical belt looks like one region. Objects between 40 and 50 AU, orbiting the Sun in the cold outer dark. But embedded within it are two populations that went through completely different experiences during the solar system's most violent period. They share the same address without sharing the same past. One population rode out the chaos, the other was shaped by it, and both are still there, sitting side by side, telling their separate stories in their orbits and their colours and the binary systems they either kept or lost. The NICE model, covered in the previous section, explains the hot classicals reasonably well. Neptune's outward migration stirred material from the inner disk into the Kuiper Belt region, producing the tilted and elliptical orbits we observe. But the cold classicals strain that explanation. Some models suggest they formed exactly where they are and simply avoided Neptune's worst influence. Others suggest there was a sharp outer edge to Neptune's migration, a point beyond which the disruption didn't fully reach. The answer is still being worked out. What is not in dispute is that the cold classicals represent something the hot classicals do not. The cold classicals are the quiet survivors of something violent, objects that somehow avoided the chaos when the rest of the disk was being scattered and ejected, and their orbits still carry that story in their geometry. Beyond the classical Kuiper Belt, there is a second region that extends much farther outward and contains objects that don't follow any of the rules the main belt objects play by. The classical belt sits between roughly 30 and 50 AU from the Sun. It is vast by any human measure, but it has boundaries. The scattered disk does not respect those boundaries. Objects in the scattered disk have orbits so elongated that their paths carry them from the inner edge of the Kuiper Belt all the way out to hundreds of AU, and in some cases, close to 1,000. These are not quiet, circular, well-behaved orbits. They are wild ellipses that swing an object from the edge of Neptune's neighborhood into the deep outer solar system and back again over timescales that dwarf recorded human history. The mechanism behind this is Neptune. When an icy body in the outer solar system had the misfortune of passing close enough to Neptune, the planet's gravity did not simply tug at it gently. It grabbed the object and flung it. Most of those objects were thrown completely out of the solar system, gone forever. But a fraction were thrown onto these extreme elongated paths instead, sent looping outward to enormous distances before gravity slowly pulled them back. Those survivors became the scattered disk. Their orbits carry the fingerprints of that ancient violent encounter, stretched and tilted in ways that make them instantly distinguishable from the cold classicals sitting undisturbed nearby. The scattered disk is, in a very direct sense, Neptune's debris field. The most prominent resident of the scattered disk is Eris. When astronomers discovered Eris in 2005, it upended everything. Here was an object slightly smaller than Pluto, sitting in the scattered disk, with an orbit that takes it out to nearly 100 AU at its most distant point and back into about 38 AU at its closest. Its year lasts roughly 559 Earth years. Eris has a moon, Dysnomia, and its surface is among the most reflective in the solar system, covered in methane ice bright enough to be seen from Earth. When its mass was measured, it came in slightly higher than Pluto's. That measurement is what forced the conversation in 2006. If Pluto was a planet, Eris had an equal or stronger claim. The solar system's definition couldn't hold both of them as planets alongside the growing list of large objects beyond Neptune, and the IAU eventually drew a line that cut them both out of the planetary category. But Eris itself had nothing to do with any of that politics. It just kept orbiting, enormous and cold, far out in the scattered disk. indifferent to what humanity decided to call it. The scattered disk thins out as it extends further from the Sun, but it doesn't stop cleanly. At its outermost reaches, it starts to blur into another structure entirely, the inner Oort cloud. The Oort cloud is a vast spherical shell of icy objects extending tens of thousands of AU from the Sun, and its innermost boundary meets the outer edge of the scattered disk somewhere in a region that has no sharp line. Some objects occupy that transition zone and don't fit comfortably in either category. The boundary is real in a mathematical sense, but in practice it dissolves under close inspection. This ambiguity matters because it means the solar system's structure does not divide neatly into labelled boxes. It is a continuum, with populations of objects gradually shading into one another as distance increases. Then there is Sedna. Discovered in 2003 by Mike Brown, Chad Trujillo and David Rabinowitz, Sedna is one of the most confounding objects in the solar system. Its orbit is extraordinary. At its closest approach to the Sun, Sedna comes no nearer than 76 AU. Its most distant point is somewhere around 937 AU. Its orbital period is estimated at roughly 11,400 years. These numbers are almost incomprehensible. At perihelion, Sedna is already far beyond anything in the classical belt. At aphelion, it is wandering the edge of the inner Oort cloud. It sits in a no-man's land between structures, and no clean model fully accounts for its presence there. Here is why Sedna is unsettling. Neptune's gravitational reach, strong enough to scatter objects throughout the disk, does not extend to 76 AU. For Neptune to have scattered an object, it needs close encounters, and close encounters only happen when objects pass through Neptune's neighbourhood. Sedna never comes anywhere near Neptune's orbit. Its closest point is already 46 AU farther out than Neptune sits. Neptune cannot have scattered Sedna. Something else put Sedna where it is, and figuring out what that something else was has driven serious scientific debate for 2 decades. The leading candidates include a close stellar encounter in the early solar system, a passing star that perturbed the outer disk before the Sun left its birth cluster. Others have proposed a distant undiscovered planet, massive enough and far enough out to have stirred objects into extreme orbits. Neither explanation has been confirmed. Neither has been ruled out. A second object with Sedna-like orbital properties, 2012 VP113, was found in 2014, and its orbit clusters in a way that strengthens the case for some external influence rather than weakening it. The statistics of these extreme orbits are not random. Something shaped them. Sedna in particular has an orbit so extreme. Its closest approach to the Sun is farther than anything in the classical belt, that Neptune alone cannot have put it there, and that implication has not gone away. When astronomers started tallying up the large objects beyond Neptune in the 2000s, the numbers kept coming in higher than the models had predicted, and at some point the conversation about Pluto being a peculiar loner simply stopped being tenable. Before 1992, the assumption was simple. Pluto was an outlier, a frozen oddball that had somehow ended up far past Neptune, alone, with no real context. That assumption collapsed quickly once the Kuiper Belt started giving up its secrets. By the mid-2000s, astronomers weren't finding one large object out there, or two. They were finding a population, the whole class of bodies large enough to be round, massive enough to matter, and strange enough individually that each one forced a new conversation about what the outer solar system actually is. The first serious challenge to Pluto's singularity came in 2005. Mike Brown and his team at Caltech announced the discovery of Eris, a body so large it appeared, initially, to be bigger than Pluto itself. Later measurements put Eris at roughly 2,326 kilometers in diameter, just slightly smaller than Pluto's 2,376. But Eris is significantly more massive. It sits in the scattered disk on an extreme elliptical orbit that takes it out to nearly 97 AU at its farthest point, well beyond the classical Kuiper Belt. Eris is covered in a bright reflective surface of frozen methane, giving it one of the highest albedos of any known body in the solar system. It has one moon, Dysnomia. The discovery of Eris is what directly forced the 2006 IAU vote, because if Pluto was a planet, Eris had an equal or stronger claim, and nobody wanted to start calling everything in the Kuiper Belt a planet. Then came Makemake, announced the same summer as Eris on July 29, 2005. Makemake is the third largest of the recognized Kuiper Belt dwarf planets, about 1,430 kilometers across. Its surface is reddish and covered in frozen methane and ethane. For years it appeared to be completely alone. No moon, no companion, nothing. Then in 2016, the Hubble Space Telescope caught something. A small, very dark moon orbiting Makemake, now called MK2. The reason it had gone undetected for so long is that MK2 is almost perfectly black, with a surface that reflects almost no light. It had been hiding in the glare of its much brighter parent body. The discovery was a reminder that even in a region we think we've mapped, objects can stay invisible simply by being the wrong color at the wrong distance. Haumea is the strangest of them all. It is roughly the same size as Pluto in terms of mass, but its shape is nothing like Pluto's. Haumea rotates faster than any other known large body in the solar system, completing a full rotation in just under 4 hours. That spin rate has pulled the object into something closer to an elongated ellipsoid, wider than it is tall, flattened at the poles, stretched at the equator. From above it would look like a rugby ball. Beyond the shape, Haumea has 2 moons, Hyakka and Namaka, and something even more unexpected, a ring, a thin dark ring of material orbiting Haumea, discovered in 2017. It was the first ring system found around a trans-Neptunian object, and it raised an immediate question. If a body this small and this far from the Sun can sustain a ring, what else out there is carrying structure we haven't detected yet? Quaoar was found in 2002 by the same team that would later discover Eris. It measures about 1,110 kilometers across and sits in the classical Kuiper Belt at roughly 43 AU. It has its own moon, Waywat, and in 2023, astronomers confirmed something about Quaoar that should not be possible. It has a ring, not at the distance where ring physics allows rings to form and persist, but farther out, well beyond what is called the Roche limit, the boundary inside which tidal forces prevent material from clumping together into moons. Everything we knew about how rings form suggested that material at Quaoar's ring distance should have accumulated into a small moon long ago, not remained as a diffuse band of particles. The ring is there anyway. Beyond these 4, there are others. Sedna, technically in an extreme orbit that puts it in its own category, is roughly 1,000 kilometers across. Orcus and Ixion sit in the 900-kilometer range. Varuna, discovered in 2000, measures around 500 kilometers. At least 7 bodies have been identified in the comparable to Pluto size class, depending on how you draw the line. Some researchers put the number higher. Before the Kuiper Belt was confirmed, planetary scientists expected the outer solar system to be nearly empty past Neptune. The discovery that it holds not one, but a whole collection of large, round, geologically distinct worlds changed the picture completely. These weren't specks of ice. They were worlds. Small ones, distant ones, frozen ones, but worlds with moons and rings and chemistry that had been sitting in the dark, unchanged, for 4.5 billion years. Each one that turned up forced astronomers to revise not just the catalogue, but the underlying assumptions about how solar systems form and what counts as a significant body. The numbers are still coming in. Vera Rubin Observatory, when it reaches full operation, is expected to find hundreds more. There may be dozens of Pluto-scale objects still undetected in the outer scattered disk, too faint and too slow-moving to have shown up yet. The population we know today is almost certainly not the population that exists. Quaoar has a ring sitting in a position where the physics of ring formation says a ring cannot persist, which means either the physics is missing something or the ring is younger than anyone expected, and neither answer is comfortable. For 76 years after its discovery, Pluto sat at the edge of the known solar system as the lonely ninth planet, and almost everything assumed about it turned out to be wrong. Clyde Tombaugh found it on February 18, 1930, at the Lowell Observatory in Flagstaff, Arizona. He was 24 years old and had been hired specifically to do the tedious, painstaking work of comparing photographic plates of the same patch of sky taken on different nights. If something had moved between exposures, it wasn't a star. It was something in the solar system. Tombaugh had been at it for about a year when a faint dot shifted position between two plates taken in January. He knew immediately that something was there. The announcement came weeks later, and the world named it Pluto, after the god of the underworld. Fitting, given how dark and cold and remote it was. The problem started almost immediately. Estimates of Pluto's mass began high and kept getting revised downward. Early calculations suggested it might be Earth-sized, which would explain why it had been detectable at all. Then better measurements put it smaller, then smaller still. By the 1970s, astronomers had determined that Pluto had no detectable atmosphere and almost certainly no satellites. By 1978, James Christie at the United States Naval Observatory noticed a recurring bump in the blurred photographic images of Pluto and identified it as a moon, which was named Charon. That discovery actually made things worse, not better, because Charon's orbit allowed astronomers to calculate Pluto's mass with far more precision than before. The answer came back startlingly small. Pluto was not Earth-sized. It was not even close to art. H-sized. It massed less than 1/5 of 1% of Earth. Less than the Moon. Far less than anyone had expected a planet to be. The awkward question of what exactly Pluto was began forming in the background of planetary science well before 1992. When Jane Liu and David Jewett discovered 1992 QB1, that question got a great deal louder. Here was an icy object orbiting the Sun at roughly the same distance as Pluto, with a similar composition. If 1992 QB1 was a Kuiper Belt object, then what was Pluto? For more than a decade after that discovery, the scientific community largely avoided the direct confrontation. Pluto remained listed as the 9th planet, but the population of known Kuiper Belt objects kept growing, and several of them were approaching Pluto in size. Then in 2005, Mike Brown and his team at Caltech announced the discovery of Eris, a body in the scattered disk that appeared to be larger than Pluto. That forced the issue. You could not call Pluto a planet and ignore Eris. Either Eris was also a planet, which would open the door to dozens more, or something had to change. The IAU vote in 2006 stripped Pluto of its planetary status. That story belongs to the next part of this series. What matters here is what scientists actually knew about Pluto by the time that vote happened, which, if you are being honest about the observational record, was almost nothing. Pluto was a blurry dot. Even the Hubble Space Telescope, trained on it at maximum resolution, could make out only vague patches of light and dark on its surface. The temperature was somewhere around -375 degrees Fahrenheit. It had a thin atmosphere of nitrogen that seasonally froze out onto the surface and then sublimated back into gas. That was roughly the extent of detailed knowledge about this object that had been classified as a planet for 76 years. Then New Horizons arrived. The spacecraft had been travelling for 9.5 years when it made its closest approach on July 14, 2015. passing within about 7,750 miles of Pluto's surface at a speed of more than 30,000 miles per hour. It could not slow down. It could not orbit. It had one pass, one chance to point its instruments at the surface and record everything it could in the few hours of close approach. What the cameras sent back stopped planetary scientists cold. Pluto had mountains, not small ones, ranges of peaks rising nearly 11,000 feet above the surrounding terrain, built from water ice hard as rock at those temperatures, strong enough to hold significant elevation over billions of years. That alone was unexpected. Bodies this small, this far from any significant tidal heating source, are not supposed to maintain geological structures. They are supposed to be ancient, cratered, dead. But the surface wasn't cratered everywhere. There was a vast plain in the western half of a bright, heart-shaped region that covered nearly 1 million square miles. The plain, named Sputnik Planitia, sat inside the larger feature that was officially designated Tombor Regio, named for the man who spent a year staring at photographic plates to find it. Sputnik Planitia was covered in slowly churning cells of nitrogen ice, convecting up from below and cycling back down like a frozen lava lamp moving over geological timescales. This kind of active convection requires heat from within. On a body the size of Pluto, this far from the Sun, there is no obvious explanation for where that internal heat is coming from. The possible subsurface ocean made it stranger still. Several lines of evidence from New Horizons data suggested that beneath the icy crust, Pluto might harbour a liquid water layer, kept fluid by the decay of radioactive elements in the rocky core. A liquid ocean on Pluto, a world that had been casually described as a frozen ball for decades, turned out to be harbouring conditions that, at least in principle, raised questions nobody was prepared to answer in 2015. Tombor had found a dot. New Horizons found a world that scientists had written off as a simple frozen ball turned out to be geologically alive, and the fact that it took until 2015 to find that out is a precise measure of how hard this region of space is to reach. In August of 2006, 424 members of the International Astronomical Union voted on a question that had been building for a decade, and by a margin that was neither unanimous nor even close to comfortable, Pluto lost its planet status. The number matters. There were roughly 10,000 IAU members at the time. Of those, about 2,700 attended the Prague conference where the vote was held. Only 424 actually cast a ballot on the final resolution. That means the demotion of a world that had been a planet for 76 years was decided by fewer people than fill a medium-sized lecture hall. The astronomers who voted to keep Pluto as a planet, and there were hundreds of them, largely did so because they believed the process itself was flawed. Many had already left the conference by the time the final vote came through. The result was real, but it was not clean. To understand what the IAU actually decided, you need to know the 3 criteria they wrote into their new definition. A planet, according to the 2006 resolution, must do 3 things. It must orbit the Sun. It must have enough mass for its own gravity to pull it into a roughly spherical shape. And it must have cleared the neighbourhood around its orbit of other debris. Pluto passes the first 2 without argument. It orbits the Sun. Its gravity has pulled it into a sphere. The 3rd criterion is where everything falls apart, and the reason it falls apart is sitting right outside Pluto's orbit in every direction. The Kuiper Belt is not incidental to this argument. It is the argument. Pluto does not orbit in a lane of empty space. It orbits inside a region crowded with hundreds of thousands of icy objects, many of them following similar paths at similar distances from the Sun. Pluto has not scattered them, captured them, or cleared them out. It simply coexists with them, which under the IAU definition is exactly what a dwarf planet does, and a full planet cannot. The Kuiper Belt, in this framing, is the physical evidence that disqualifies Pluto from the category it held for most of the 20th century. This is the part that stung. It wasn't that some distant committee decided Pluto was small. It was that the solar system itself provided the evidence against it. The moment Jewett and Liu confirmed in 1992 that Pluto had neighbours, the reclassification became a matter of when, not whether. Every additional Kuiper Belt object discovered between 1992 and 2006 made the argument stronger. By the time the IAU convened in Prague, Eris had been found, an object nearly identical in size to Pluto, orbiting in the same general region. If Pluto was a planet, then Eris was a planet. And if Eris was a planet, astronomers started running the numbers on how many other objects might eventually qualify. The answer was uncomfortable enough that the committee knew something had to change. The public response was not what the IAU expected. School children sent letters to observatories. Protest signs appeared outside planetariums. The state of New Mexico officially declared that Pluto remained a planet within its borders, which is not a power states actually have over orbital mechanics, but illustrated something real about how people felt. Pluto had been on the solar system poster in every classroom since 1930. It had a name people could pronounce and a story connected to the man who found it. Stripping that felt personal in a way that scientific reclassifications rarely do. The scientific objection, though, was more serious than the public one. A significant group of planetary scientists never accepted the IAU definition, and their objection was not sentimental. Their argument focused on the third criterion, clearing the neighbourhood, and the way it scales with distance from the Sun. An object at 40 AU orbits in a region geometrically far larger than an object at 1 AU. The sheer volume of space to be cleared grows with distance. Under the IAU's criterion, a body like Pluto faces a mathematical disadvantage simply because it orbits far from the Sun, not because it is fundamentally different in character from objects closer in. Earth, at 1 AU, clears its neighbourhood relatively easily. Pluto, at 39 AU, would need to dominate a vastly larger volume. Some researchers argued this makes the criterion physically arbitrary rather than physically meaningful. Alan Stern, who led the New Horizons mission to Pluto, has been among the most persistent critics. His argument takes a different angle. Pluto, as revealed by the 2015 flyby, is more geologically active and more internally complex than several of the 8 recognized planets. It has nitrogen glaciers, apparent tectonic features, a layered atmosphere, and evidence pointing toward a liquid water ocean beneath its ice shell. Mars, a recognized planet, is geologically quieter than Pluto by most current measures. Mercury has far less going on at its surface. The idea that geological complexity should factor into the definition has not been adopted by the IAU, but it has not gone away either, and Stern and his colleagues have proposed alternative definitions based on physical properties rather than orbital dynamics. The counterargument from the IAU side is that the definition needs to be workable. If you define planets by geological complexity or internal differentiation, you open the door to classifying large moons as planets. Europa, Titan and Ganymede would all qualify under certain proposed definitions. The IAU chose orbital dynamics because the criterion produces a consistent and manageable list. Whether that list reflects physical reality or administrative convenience is exactly what the argument is about. The debate has not closed. There are still working planetary scientists who think the IAU definition was poorly constructed and that the reclassification will eventually be revisited, and the Kuiper Belt is at the centre of that argument. The only spacecraft that has ever visited the Kuiper Belt was launched nearly 2 decades ago, and the speed it was travelling, the fastest any human-made object had moved at launch up to that point, still wasn't fast enough to make the journey feel short. New Horizons lifted off from Cape Canaveral on January 19, 2006. The same month, the IAU debate about Pluto was accelerating towards its August vote. The timing was not lost on anyone. NASA had committed billions of dollars and years of engineering to send a spacecraft to a world that was about to be stripped of its planetary status before the probe even arrived. New Horizons was already 9 hours into its journey when the launch team finished celebrating. It crossed the orbit of the Moon in under 9 hours. The same trip took Apollo astronauts 3 days. That number alone tells you something about how fast this spacecraft was moving, and it still needed nearly a decade more to reach its destination. The first major waypoint was Jupiter. In February of 2007, 13 months after launch, New Horizons swung through the Jovian system and used the planet's enormous gravity as a slingshot. The maneuver added roughly 9,000 miles per hour to the spacecraft's speed and bent its trajectory precisely toward Pluto. While it was there, the science team turned every instrument on and collected data on Jupiter's moons, its magnetic field, and its atmosphere. It was both a test run and a bonus mission, crammed into a few days of closest approach. Then Jupiter shrank in the cameras, and New Horizons settled in for the long crossing. 7 more years. That is what followed. The spacecraft moved at roughly 36,400 miles per hour, fast enough to cross the continental United States in under 4 minutes. And it still had to travel for 7 years before Pluto began to look like anything more than a dot. The mission team kept the spacecraft in a kind of hibernation for much of the cruise, running minimal systems to preserve hardware. Occasionally they woke it up, ran diagnostics, checked instruments. Then they put it back to sleep. The engineers who had built it were aging. Some retired. The project kept going. By 2015, Pluto was finally resolving into something real. Images coming back in the months before closest approach showed a round world, clearly differentiated, with what looked like surface features. People who had waited their entire careers for this were watching a planet, or former planet, come into focus for the first time. The closest approach happened on July 14, 2015. New Horizons passed within 7,750 miles of Pluto's surface. Moving so fast, there was no question of slowing down or orbiting. It had one pass. Everything the science team wanted had to be captured in a window of hours. The spacecraft's antenna was pointed at Pluto during the flyby itself, not at Earth, which meant that for a full 22 hours after closest approach, no one on the ground knew if everything had worked. The signal confirming success arrived late on July 14th. The team erupted. The images started coming in. What the images showed was not the simple frozen ball anyone had assumed. But there was an immediate problem. New Horizons was now 3 billion miles away. At that distance, radio signals traveling at the speed of light take about 4.5 hours to make the one-way trip. The spacecraft's transmitter was not powerful. The antenna was the size of a large dish, but the signal arriving at Earth was so faint it required the largest receivers in NASA's deep space network to detect it. The data transmission rate was slower than a dial-up modem from the early 1990s. It took 16 months to fully download everything the spacecraft had collected during its few hours near Pluto. 16 months. For a flyby that lasted one afternoon. The mission wasn't finished. While the Pluto data was still trickling down, the team was already looking ahead. They had identified a target in the outer Kuiper Belt, a cold classical object designated 2014 MU69, later named Arrokoth. Reaching it required New Horizons to fire its engines and shift course. The spacecraft had limited fuel. The maneuver had to work precisely, because there was no second option. In 2015 and 2016, the team executed a series of 4 engine burns that redirected New Horizons onto an intercept trajectory with Arrokoth, more than 1 billion miles farther out than Pluto. The spacecraft crossed the orbit of Pluto and kept going. New Year's Day, 2019. New Horizons flew past Arrokoth at a distance of about 2,200 miles, farther from Earth than any object humanity had ever visited up close, 43.4 astronomical units from the Sun. The images arrived slowly, in pieces, over months. What they showed was unlike anything in the planetary science catalogue. But that story belongs to the next chapter. After Arrokoth, New Horizons continued outward. The instruments kept running. The team kept looking for additional targets, searching the deep Kuiper Belt for anything the spacecraft might be able to observe at long range. The power supply, a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity, is slowly fading, losing a few watts every year. At some point, perhaps in the 2030s, there will not be enough power left to run the science instruments. Until then, the mission continues. New Horizons is still out there, still moving, its instruments still online, and the signal it sends back now takes so long to arrive that the mission team has to plan observations hours in advance of when they want them to happen. The most important object in the Kuiper Belt may not be Pluto. It may be a lumpy red two-lobed shape about 35 kilometers across that most people have never heard of. After New Horizons completed its Pluto flyby in July of 2015, the mission team had a choice to make. The spacecraft was still moving outward, still operational, and there was fuel left. They could point it deeper into the Kuiper Belt and attempt something no mission had ever done before. Visit a cold classical Kuiper Belt object, one of those undisturbed primordial bodies sitting quietly where they had sat since the solar system formed. The team searched the sky for a candidate within reach of the spacecraft's adjusted trajectory. They found one, a small object designated 2014 MU69, sitting 43.4 astronomical units from the Sun. The Powhatan word for sky is Arrokoth. That became its name. On January 1st, 2019, New Horizons flew past it at a distance of just 3,500 kilometers, closer than it had passed Pluto, and the images that came back changed how planetary scientists think about the earliest moments of solar system formation. What the cameras showed was unexpected. Not a rough sphere, not a battered, cratered ball. What New Horizons sent back looked like two reddish flattened lobes pressed together at a narrow neck, like a lumpy snowman that someone had partially sat on. Each lobe had its own name. The larger one was called Ultima, the smaller one was Thule. Together they formed what astronomers call a contact binary, two distinct objects that are now touching, connected at a single point of merger. The reddish colour was immediate and striking. That colour comes from tholins, complex organic molecules that form when simple chemicals like methane and water ice are bombarded with radiation over billions of years. Arrokoth had been sitting at 43 AU in near-perfect cold for 4.5 billion years, and the rad, Aeation, had been slowly doing chemistry on its surface the entire time. The shape was the clue that mattered most. A contact binary tells a story about how it formed, but the story depends entirely on how those two lobes came together. There are two possibilities. The violent version, two separate objects on different orbits happened to collide at high speed, and the collision fused them. This is chaotic, energetic, and would leave behind a shattered, deformed structure with signs of impact damage. The gentle version, two objects that were already orbiting each other in a slow binary pair gradually spiraled inward over millions of years, their orbit decaying through a process called dynamical friction, until they finally touched, gently, almost like a slow drift into contact rather than a crash. Arrokoth showed no signs of a violent collision. The neck between the two lobes was smooth. The lobes themselves were intact, not fractured or crushed. The surface showed no evidence of high-speed impact debris. Everything about the shape pointed to the gentle version. Two bodies that had formed together, orbited each other for millions of years, and eventually merged so softly that neither was significantly damaged by the encounter. This was not what the older models predicted. For decades, the standard picture of planetesimal formation relied on accretion through collision. Small particles hit each other, stuck together, built up into larger clumps which hit other clumps, and gradually over millions of years, the accumulation process built objects the size of Arrokoth and eventually much larger. This requires high collision rates. At 40 AU though, the solar system is so vast and objects orbit so slowly that collision rates are extraordinarily low. The timescale problem was already uncomfortable. Arrokoth made it worse, because if the two lobes had formed separately and then collided violently, the material density at that distance should have made even a gentle collision difficult to produce over any reasonable timescale. What Arrokoth pointed toward instead was a process called streaming instability. The idea is different from the classical collision model in a fundamental way. Rather than objects building up through successive individual collisions, streaming instability proposes that clouds of small particles, pebbles essentially, concentrated into dense filaments through a kind of feedback between the particles and the gas of the early protoplanetary disk. Once the concentration crossed a threshold, gravity took over and the whole cloud collapsed directly into a gravitationally bound clump. Not through thousands of individual collisions, but through one collective collapse. And in the right conditions, that collapse naturally produced not one object, but two, a binary pair, orbiting each other from the moment of their formation. Two lobes, born together, drifting slowly toward each other over millions of years. This is Arrokoth's shape, explained from first principles. The implications reach far beyond one small frozen object at 43 AU. If streaming instability is how objects formed in the cold classical Kuiper Belt, then the violence that older models assumed, the constant high-speed collisions, the shattered precursor bodies, the chaotic early accumulation, may never have happened out there at all. The cold classicals may have formed gently, quietly, in near-perfect gravitational harmony, and then been left alone while the rest of the solar system went through its turbulent early history. Arrokoth survived that history intact. Its shape was not disturbed. Its surface was not reshaped by heat or impact. It preserved, frozen at -220 degrees Celsius, the exact geometry of its formation. No object ever studied up close has been less changed by time. Arrokoth is not just the most distant object ever visited. It is the most unchanged object ever visited. And what it looks like tells us that the Kuiper Belt formed more gently than any previous model had predicted. The surface of a Kuiper Belt object is one of the most chemically preserved environments in the entire solar system. The reason for that is simple. Nothing has disturbed it in 4.5 billion years. No geology, no atmosphere, no liquid water reshaping the surface over time. The objects sitting out there at 40 or 50 AU from the Sun have been exposed to nothing but cold, darkness. The faint trickle of radiation from a star so distant it looks like a bright point of light. That combination has locked their chemistry in place with a precision that nothing closer to the Sun can match. Arrokoth showed us the shape of how these objects formed. The chemistry tells us what they are made of. The basic inventory is not complicated. Water ice is the dominant component across most Kuiper Belt objects. Beyond that, methane ice, ammonia ice, carbon monoxide ice fill out the composition in varying proportions depending on the object and where it formed in the original disk. These are molecules that would not survive in solid form anywhere near Earth. Bring methane ice into the inner solar system and it sublimates. It turns directly into gas and disperses. At -369 degrees Fahrenheit, which is the average temperature across the Kuiper Belt, none of that happens. The volatiles that would boil away in warmer environments are frozen solid and have been frozen solid since before the planets fully formed. This is what makes the Kuiper Belt a chemical time capsule. The materials sitting on the surface of a cold classical KBO today are chemically close to identical to what was floating in the protoplanetary disk 4.5 billion years ago. There is something stranger on the surface though, and it has to do with colour. Many Kuiper Belt objects are not white or grey, the way you might expect pure ice to look. They are red. Some of them are deeply, vividly red, the colour of rust or dried clay or oxidized iron. That colour is not coming from iron. It is coming from a class of organic molecules called tholins. When radiation, cosmic rays, solar ultraviolet light, energetic particles from beyond the solar system hit simple molecules like methane and nitrogen ice, it breaks the molecular bonds and drives those fragments into new combinations. Over millions of years, that process builds up complex organic polymers on the surface of any icy body that sits exposed in the outer solar system. Those polymers are tholins, and they are reddish-brown. The longer the surface has been sitting in radiation, the more tholins accumulate. The redder the object appears. The deep red colour on Arrokoth, on many cold classical KBOs. On the surface of Pluto's moon, Charon in its polar regions. All of it is a direct record of billions of years of radiation chemistry, written in colour, visible from Earth through a telescope. What you cannot do easily from Earth is read the full chemical story. Spectroscopy is the main tool. When light from the sun reflects off a KBO and travels back to a telescope on Earth, the spectrum of that reflected light carries fingerprints of whatever chemicals are on the surface. Different molecules absorb light at different wavelengths. Match the absorption pattern against a known library of chemical spectra, and you can identify what is there. In practice, at 40 AU, the objects are so faint and so far away that the signal is weak. Water ice has a strong, identifiable spectral signature and shows up clearly. Methane ice has been confirmed on several larger objects, including Pluto and Make. Ammonia ice has been detected on Charon, but for the smaller, dimmer objects that make up the majority of the belt's population, the signal barely rises above the noise. There are almost certainly chemical compounds out there that no telescope has resolved yet because the objects are simply too dim. This is where comets become useful. Short-period comets, the ones with orbital periods under 200 years, the ones that travel roughly in the same plane as the planets, are thought to originate in the Kuiper Belt. A gravitational nudge from Neptune destabilizes a KBO's orbit and sends it inward on a new trajectory. As it falls toward the sun, it warms up. The ices that have been frozen on its surface since the formation of the solar system begin sublimating, releasing gas and dust in the bright expanding cloud called a coma. What that comet is venting into space is Kuiper Belt chemistry. It is the interior material of an object that has been sealed since the beginning. Studying that outgassing, which astronomers can do in extraordinary detail even from Earth because the comet is now close, gives an indirect window into the composition of the belt itself. Missions like Rosetta, which orbited comet 67P in close proximity for 2 years, detected complex organic molecules that had never been seen in space before, including glycine and amino acid. That is Kuiper Belt chemistry arriving in the inner solar system after a journey of billions of miles. When a comet swings past the sun and its ice starts sublimating into a tail, what you are seeing is Kuiper Belt material experiencing sunlight for the first time, and the chemistry being released was locked in place when the solar system was still forming. Among all the populations of small bodies in the solar system, the Kuiper Belt has by far the highest fraction of objects that turn out to be twins. 2 bodies of roughly equal size, orbiting each other rather than one object orbiting another. This is not a minor statistical quirk. Roughly 80 known Kuiper Belt objects are classified as true binaries, meaning both components are comparable enough in size that calling one of them a moon would be misleading. They are pairs, and the cold classical population, that quiet undisturbed population sitting in its low inclination orbits, has a binary fraction that is dramatically higher than anything seen in the asteroid belt or among the scattered disk objects. In some surveys of cold classicals, more than 30% of the objects examined turned up to be binaries. Nowhere else in the solar system comes close to that. The first thing that number demands is an explanation. How do you get so many paired systems in one region? There are two basic ways a binary can form. Either two objects form separately and then get captured into orbit around each other through some gravitational interaction, or they form together from the beginning, emerging as a pair out of the same cloud of material. Capture is a messy process. It requires a third body to carry away excess energy at exactly the right moment, and in the cold classical belt, which is not a crowded environment, accidental three-body encounters should be rare. Capture cannot explain 30%. That number points strongly toward the second option. These pairs were born together. What makes the cold classical binaries particularly striking is their geometry. The separations between the two components are wide, sometimes surprisingly wide, with the two bodies circling each other at distances of tens of thousands of kilometers. Their masses are nearly equal. Their orbits around each other tend to be roughly circular and prograde, meaning they spin in the same direction as their mutual orbit around the Sun. That whole package, wide separation, equal mass, circular prograde orbit, is exactly what you would expect if both components condensed out of the same collapsing cloud of material at the same time. It is not what you would expect from a chaotic capture event. This is where the formation picture gets genuinely interesting. The process that best fits the binary statistics is called streaming instability. The idea is that in the early solar system's outer disk, small solid particles drifting through the gas did not collide and stick one by one to build up large objects slowly over millions of years. Instead, under certain conditions, those particles concentrated themselves into dense filaments and clumps, and when a clump became dense enough, it collapsed under its own gravity directly into a bound object. Sometimes that collapse produced a single body. Often it produced two. The angular momentum of the original cloud naturally encouraged the material to settle into a rotating pair rather than a single spinning mass. Streaming instability was a theoretical proposal for years before the observational evidence started stacking up behind it. The binary statistics from cold classical KBOs were part of that evidence. Then Arrokoth arrived, and the picture sharpened considerably. Arrokoth, as discussed in this series, is a contact binary, two lobes that were once a wide binary pair before slowly spiraling together and gently merging. The key word is gently. There is no sign of a violent collision on Arrokoth's surface. The two lobes fit together in a way that implies a soft, slow approach over a very long time, not an impact. That is exactly what streaming instability predicts. A cloud collapses. Two objects form. They orbit each other, gradually losing energy, and eventually touch. No catastrophe required. The contrast with older models is stark. For most of planetary science's history, the dominant assumption was that planetesimals grew through accretion, small objects smashing into each other, fragmenting, reaccreting, gradually building larger bodies through repeated violent collisions. That model has its merits in the inner solar system, where collision velocities are higher and the disk was denser and warmer. But in the outer disk, at 40 to 50 AU, the math never worked cleanly. Collision rates were too low, relative velocities too slow, and the timescales before the disk dispersed were too short to build objects as large as Pluto through incremental collision alone. Streaming instability sidesteps the problem. It does not need millions of collisions. It needs one gravitational collapse, and the binary systems sitting out in the cold classical belt, wide and equal and undisturbed, are the preserved evidence that this is how things actually happened. Their orbits have not been scrambled by Neptune. Their compositions have not been altered by heat. They are the original product of formation, still in roughly the shape they were in 4.5 billion years ago. If the cold classicals formed the way the binary statistics suggest, then the building blocks of planets were assembled more gently and more efficiently than the collision-dominated models that dominated planetary science for decades. Every few decades, a comet swings through the inner solar system and becomes visible to the naked eye. In most cases, the chain of events that sent it inward from its frozen resting place traces back to the Kuiper Belt. That connection is not obvious when you are standing outside watching a comet cross the sky. It looks like a single dramatic event, a bright nucleus, a tail stretching across several degrees of arc, light that has no business being there. But that moment is the end of a process that started billions of miles away. It started with a nudge. Neptune's gravity is constantly working on the objects in the Kuiper Belt. Most of them hold their orbits without incident for millions of years, but some sit in orbital configurations that are slightly unstable. And over long timescales, those orbits shift. The object drifts closer to Neptune's reach. Neptune pulls on it. The object's path becomes more elliptical, more tilted. Eventually, after enough gravitational interference, the orbit stretches inward. The object begins a journey toward the sun that it has never made before. This is the pipeline, not a fast process, not a dramatic one at any single moment, but it is relentless, and it has been running for 4.5 billion years. The comets that arrive through this pipeline carry a specific signature. They have orbital periods of less than 200 years. They tend to travel in roughly the same plane as the planets, with low inclinations. Astronomers call them short-period comets. Within that category, the most numerous group carries an even more specific name: Jupiter family comets. These are comets with periods typically shorter than 20 years. Their orbits are shaped by Jupiter's gravity at the inner end of their journey. Comet Halley travels on a longer period, closer to 75 years. Its origin is genuinely debated. Some researchers place it in the scattered disk at the outer edge of the Kuiper Belt region. Others point toward the inner Oort cloud. It does not fit cleanly into either box, which is itself telling. But the Jupiter family comets do fit cleanly. Their orbital properties match exactly what you would expect if they originated in the Kuiper Belt and were scattered inward by Neptune. Dynamical models can trace their orbits backward in time and point them home. The Kuiper Belt, specifically the scattered disk component, is the reservoir from which they came. This is not speculation. It is the result of decades of computer simulations, orbital mechanics analysis, physical observation, all pointing toward the same source. Now here is why this matters beyond the simple pleasure of watching a comet. When a comet gets close enough to the Sun, its frozen surface starts to sublimate. Ice that has been locked solid at -369 degrees Fahrenheit for billions of years suddenly encounters enough heat to convert directly from solid to gas. That gas, and the dust embedded in it, streams away from the nucleus and forms the tail you see from Earth. What you are watching when you watch a comet's tail is Kuiper Belt material being released into space for the first time. The chemistry in that tail, the water vapor, the carbon monoxide, the complex organic molecules, is the preserved chemistry of the early solar system. It has been sitting unchanged in the Kuiper Belt since before Earth existed. This is what makes the Comet-Kuiper Belt connection more than an orbital mechanics curiosity. If short-period comets are pieces of the Kuiper Belt delivered inward, then every comet that has ever struck Earth or passed through the early inner solar system was carrying Kuiper Belt chemistry with it. The water in Earth's oceans has been a subject of intense debate for decades. One hypothesis holds that comets delivered a significant fraction of it during the period of heavy bombardment in the early solar system. If that hypothesis is correct, if those comets originated in the Kuiper Belt, then the water you drink has a direct chemical ancestry stretching back to a frozen object orbiting at 40 AU. The organic molecules that preceded life on Earth may trace the same path. Not everyone agrees on the water delivery hypothesis. Measurements of the hydrogen isotope ratios in comet water have produced mixed results. Some comets match Earth's water, some do not. The debate is ongoing, but the connection between the Kuiper Belt and the chemistry of the inner solar system is real, regardless of how that specific argument resolves. Comets carry organic material. They carry complex chemistry. That chemistry was synthesized in the cold outer disk of the early solar system and preserved in the Kuiper Belt for billions of years before Neptune's gravity finally dislodged it and sent it inward. Every short-period comet visible from Earth is a small piece of the Kuiper Belt making a one-way trip toward the Sun. Most will be destroyed within a few thousand years of orbital passes. Their volatiles exhausted, their surfaces darkening into dead rock. The Kuiper Belt keeps sending replacements. The icy objects circling the Sun at 40 AU today are the source reservoir for most of the comets that have lit up the sky throughout human history. That means the Kuiper Belt has been delivering material to the inner solar system, and possibly to Earth, for billions of years. The Kuiper Belt is not the edge of the solar system. It feels like it should be. It starts 4.5 billion kilometers from the Sun, beyond the last planet, in a region so cold and dark that water ice has sat undisturbed for 4 billion years. By any measure that makes sense to a human being, it is remote. But the solar system does not end there, not even close. To understand what lies beyond, you need a number. The Kuiper Belt runs from roughly 30 to 50 astronomical units from the Sun. That distance is already staggering. 50 AU means light from the Sun takes over 6 hours just to arrive. The entire Kuiper Belt, from its inner edge near Neptune to its outer scattered disk, spans a region measured in billions of kilometers. And then there is the Oort cloud, which begins where the scattered disk fades out, somewhere around 2000 AU, and extends outward to perhaps 200,000 AU. That number is not a typo. The nearest star to our Sun sits about 270,000 AU away. The Oort cloud, if its outer boundary estimates are correct, reaches almost halfway there. The Sun's gravitational influence stretches across a sphere so vast that the entire architecture of planets, moons, asteroids, and the Kuiper Belt fits into a small warm pocket at its center. Here is a way to hold that comparison. If you shrunk the distance from the Sun to the inner edge of the Kuiper Belt down to 1 centimeter, the outer Kuiper Belt would sit about 1.5 centimeters away. The outer Oort cloud at that same scale would be sitting roughly 60 meters down the street. The Sun's reach is not a modest extension of the planetary system. It is a structure of entirely different proportions. The Kuiper Belt is a flat disk, concentrated near the plane where the planets orbit. It has thickness, some inclination, but it is fundamentally a ring, a donut shape arranged neatly around the ecliptic. The Oort cloud is nothing like that. It is a sphere, or something close to one, wrapping around the entire solar system in every direction equally. Long-period comets arrive from every angle, from above the plane, below it, from directions that have nothing to do with where the planets sit. That distribution is the evidence. If the Oort cloud had a disk shape like the Kuiper Belt, its comets would arrive from predictable directions. They don't. They come from anywhere. That near-perfect spherical distribution is what tells astronomers the Oort cloud exists, because nobody has ever seen it directly. This is worth pausing on. The Oort cloud is entirely inferred. No telescope has imaged it. No spacecraft has reached it. New Horizons, traveling at over 50,000 kilometers per hour since 2006, won't enter the Oort cloud for another 300 years, and won't exit it for roughly 30,000 years after that. The evidence for the Oort cloud comes entirely from watching where long-period comets originate, the ones with orbital periods stretching into the thousands or millions of years. When those trajectories are traced back, they point to a vast spherical reservoir at the edge of the Sun's gravitational grip. The math works. The structure is almost certainly real, but it has never been seen. The Kuiper Belt was itself invisible for most of human history. Jewett and Liu found the first confirmed object in 1992, and that discovery redrew the map. Before that, the solar system appeared to end at Neptune, or at most at Pluto. The confirmation of the Kuiper Belt moved the edge outward. Then the scattered disk pushed it further still to hundreds of AU. Then Sedna, with its perihelion at 76 AU and an aphelion possibly reaching 1000 AU, blurred the boundary between the scattered disk and whatever comes next. Each time the boundary moved, something was waiting beyond it. There is no reason to think the Oort cloud is the final answer, though at 200,000 AU it may be close to the practical limit of where the Sun can hold anything in a stable orbit. What actually fills the Oort cloud is largely unknown. Estimates suggest it contains trillions of icy bodies, similar in composition to Kuiper Belt objects, frozen remnants of the early solar system flung outward by gravitational interactions with the giant planets over billions of years. But they are too far, too cold, and too dark to observe directly. The Oort cloud is the Sun's attic, vast, full, and almost entirely unexplored. The Kuiper Belt, which seemed impossibly remote when Jewett and Liu first detected 1992 QB1, turns out to be practically in the Sun's backyard compared to what lies beyond it. Taken together, the Kuiper Belt is not just a structure at the edge of the solar system. It is a record of everything that went wrong, or maybe everything that went right, during the first billion years of our solar system's existence. Every population within it, every orbital class, every frozen binary pair sitting 40 astronomical units from the Sun, is a fragment of a story that standard accretion models spent decades trying to tell cleanly and kept getting wrong. The reason the size is so hard to explain is not a measurement problem, it is a history problem. And the history is stranger than anyone working in planetary science in the early 20th century would have guessed. Think about what the belt is actually showing you when you map it carefully. You have the cold classicals, objects sitting in nearly circular, low-inclination orbits, barely disturbed, chemically primitive, many of them paired in wide binary systems that have survived intact for 4.5 billion years. These are the undisturbed remnants. They formed close to where they sit now, in a region of the disk that somehow avoided the worst of what came later. Then, sharing the same general neighbourhood, you have the hot classicals, higher inclinations, more elliptical paths, the clear signature of something that pushed them. They were not born there, they were scattered in. Two populations, same address, completely different histories. That is not what a simple, orderly solar system product says. That is what a violent one leaves behind. The NICE model gives you a framework for reading this. Neptune did not form at 30 astronomical units. It formed closer in, and it migrated outward over millions of years as it exchanged momentum with the surrounding disk of planetesimals. As it moved, it swept material ahead of it. Some of that material was pushed into resonant orbits and carried outward with the planet. Some was scattered inward, handed off to Jupiter, and ejected from the solar system entirely. A fraction ended up in the orbits we now see in the Kuiper Belt. The hot classicals are, in a very direct sense, refugees from Neptune's migration path. Their tilted and stretched orbits are the orbital scars of that encounter. The late heavy bombardment sits inside this same story. Roughly 700 million years after the solar system formed, something destabilized the giant planets into a period of reshuffling. The inner solar system was hammered with impactors. The moon's cratered surface preserves that record. The Kuiper Belt preserves a different piece of it. The population that was left behind after the ejections, the scatterings and the resonance sweeps had finished. What survived was a fraction of what had been there before. The missing mass problem is not mysterious when you accept the violence. The mass is not missing. It was removed methodically by processes that operated on timescales of hundreds of millions of years. The ghost belt we observe today is what remained after the clearing. What makes the belt genuinely remarkable as a scientific object is that different parts of it encode different moments in that history. The cold classicals record the pre-migration disk. Their binary systems with wide separations and nearly equal masses tell you how planetesimals formed before Neptune arrived, gently through gravitational collapse rather than violent collision. The hot classicals record the migration itself. The scattered disk records the ongoing perturbations that followed, the objects still being nudged outward on long ellipses by Neptune's continuing gravitational presence. Each population is a different layer in the same geological cross-section. You are not looking at one uniform region. You are reading a stratigraphy of chaos. This is why the size is so difficult to explain through any single mechanism. A simple disk fragmentation model cannot produce the cold classicals and the hot classicals simultaneously. A simple migration model cannot account for the binary fraction in the cold classical population without invoking early formation conditions that predated the migration. The reality is that the belt's current architecture requires a sequence of distinct events, each operating on different timescales, each leaving a different imprint. The framework that explains one population creates new questions about another, and that layered complexity is precisely what you would expect from a solar system that went through multiple episodes of large-scale dynamical reshuffling in its first billion years. There is something almost counterintuitive in this conclusion. You might expect that understanding the Kuiper Belt better would make it seem more orderly, more predictable. Instead, every new population identified, every new orbital class mapped, every new binary system catalogued, adds another piece of evidence that the early solar system was far more chaotic than the clean arrangement of planets we inherited would ever suggest. The current solar system looks stable. It looks like it was always this way. The Kuiper Belt says otherwise. It is the physical evidence that the planets moved, that the disk was disrupted, that most of what formed in the outer solar system was destroyed or ejected, and that what we call normal is actually the aftermath of a catastrophe we can no longer observe die, rectly, but can still read in frozen orbits at the edge of everything. The size that seems impossible to explain is actually a direct measure of the chaos that built the solar system we live in, preserved in ice and slow orbits at the edge of the sun's reach. There is a list of open questions about the Kuiper Belt that is longer today than it was in 1992. Every answer the last 30 years produced came attached to at least one new question. That is not a failure of science. That is what happens when you start pulling at something genuinely large. The most discussed open question right now has a name that sounds almost fictional: Planet 9. A small group of researchers noticed something strange in the orbital data for a handful of extreme scattered disk objects, bodies with perihelia so distant that Neptune's gravity cannot fully account for their trajectories. The orbits of these objects cluster together in a way that seems statistically improbable. Random scattering should have spread them more evenly around the sky. Instead, they point in roughly the same direction, as if something massive and distant is herding them. Tugging their paths into alignment across billions of kilometers of empty space, the proposed object would be roughly 5 to 10 times Earth's mass, sitting somewhere between 400 and 800 AU from the Sun. On an orbit so slow, it would take 10 to 20,000 years to complete a single revolution. Nobody has seen it. No telescope has confirmed it. But the orbital clustering is real. The most straightforward explanation for it is a planet we haven't found yet. Not everyone agrees the clustering is real. Some researchers argue it's a statistical artifact of observational bias, that we tend to discover these distant objects from certain parts of the sky. That skews the apparent distribution. The debate is unresolved. It is the kind of problem that keeps orbital dynamics researchers running calculations at 3 in the morning. Sedna is its own separate problem. Its closest approach to the Sun sits at 76 AU. Nothing in the classical belt even comes close to that. Neptune can scatter objects outward, but not that far. The standard scattering models cannot put Sedna where it is. One possibility is that Planet 9, or something like it, scattered Sedna onto its current path. A third possibility is that there is a mechanism we haven't thought of yet. Sedna has been known since 2003 and still has no clean explanation. A second inner Oort cloud object, 2012 VP113, was found in 2014 with a similarly extreme orbit. The population of objects in this transition zone between the scattered disk and the Oort cloud proper is almost entirely unmapped. Then there is the formation debate. Streaming instability explains the binary statistics and the gentle accretion geometry, but the exact conditions that trigger it, the precise size of the initial particle clouds, how efficiently the process operated across the full width of the primordial disk are still being worked out. The models agree on the broad outline. The specifics are still being argued, and most of the belt itself simply hasn't been seen. The confirmed catalogue of Kuiper Belt objects runs into the thousands. The models say the true population is in the hundreds of thousands for large objects alone, into the trillions when you count everything. The gap between what we've confirmed and what should be there is not a small rounding error. It is an enormous blind spot, so cold and so far away that most of them fall below the detection threshold of every telescope that has ever looked in that direction. That is about to change. The Vera Rubin Observatory in Chile, that is beginning full operations, will conduct a decade-long survey of the southern sky with sensitivity and cadence that no previous instrument has matched. Current estimates suggest it will catalogue tens of thousands of new Kuiper Belt objects within its first few years of operation. The orbital architecture of the belt will come into focus in a way it never has before. If Planet 9's signature is real, Rubin should sharpen it. If it's a bias artifact, Rubin's more uniform sky coverage should wash it out. On a clear night, the light arriving from the direction of the Kuiper Belt has been travelling for 4 to 5 hours just to reach the edge of the inner solar system. Longer still to reach you. The objects out there are moving so slowly that a full orbit takes more than 2 centuries. The cold classical belt objects have been circling in nearly the same paths since before Earth had oceans. Nothing has touched them. Nothing has changed them. They are the most pristine material in the solar system, sitting at distances that have kept them beyond reach for the entire span of human history. We have visited exactly one of them at close range. The Kuiper Belt has been out there since before the Sun finished forming, unchanged and patient. We are only just beginning to read what it has been waiting. NG this whole time to tell us.